So in the last video, we showed that, we defined the empty set, and we showed that it deserves at least a part of its name. We showed that it deserves to be called empty. So we justified the word empty, but does it deserve to be called the empty set? In this video, we're going to justify the word the. So here's Theorem 14. If x is not an A for all x, then A equals the empty set. So here it is symbolically. If for all x not an A, if this, then A equals the empty set. In other words, if A has nothing in it, then A is the empty set. So this is a way of saying that the empty set is the only empty set. If you think of empty as meaning has no elements. So this left-hand side here says A has no elements, right? For all x is not an element of A. So A has no elements. Then overall this theorem is saying if A has no elements, then A is the empty set. A is this guy. Do you see how this is a way of saying that the empty set is the only set that has no elements? If you thought you had a different one, a different set that also has no elements, then, well, according to Theorem 14, it would just be the empty set again. It wasn't really different after all. So this justifies calling it the empty set. So at the beginning, when I just introduced the symbol and the semantics, this was just a title. We just called it the empty set. That was its name. We didn't justify the individual phrases that we were using. But these theorems justify that the name is a good name. Okay, so proof. Now, what do I have? It's an implication, right? If you look at it symbolically, that's very clear that at the top level we have an implication. But even looking in words, it's an if-then statement. So I should assume the hypothesis, the left side of the implication, and then attempt to prove the conclusion. So assume that, let me just write it symbolically, that nothing is in A. Assume that nothing is in A. Then what can I do? And what am I trying to do? So I'm trying to prove that A equals the empty set. Maybe I should have a goal stack here. So let me keep track of my goals here. So this is scratch work that I would definitely not include in my final draft. I would keep this a secret, but I'm just showing it for demonstration. Okay, so my goal is to prove A equals the empty set. So I'm going to assume this, and I feel stuck. Okay, so I need to break down my goal. That's one way to get unstuck. And I also need to think about how can I use what I have. What I have is a universal. Nothing is in A. Everything is not in A. Sorry, what I have is a typo, actually. There. Everything is not in A. So to use this, I would have to use universal instantiation. Apply it to a specific case. So given any particular thing, that thing is not in A. Right now, I don't have anything to apply it to. So let me forget about this for a sec and think about breaking down my goal. How am I going to prove an equality? Prove that A equals the empty set? Well, there's one axiom called equality gained. Here, Axiom 8. It says, if I can prove that being an element of one thing is equivalent to being an element of the other thing, then the two things are equal. So this is one approach. I could try to prove this equality, that A equals the empty set, by proving that being an element of A is equivalent to being an element of the empty set. What is usually easier than trying to prove a double arrow, and what you'll see done more commonly, is Theorem 10. So prove this equality by proving both inclusions. And that will break it down into two more manageable pieces. So I actually recommend using Theorem 10 unless you see a very clear, immediate way of using Axiom 8. Theorem 10 will break it down into more manageable pieces. So in some sense, I have split the goal in two. So now my goal is to prove A subset empty set and empty set subset A. So I have these two inclusions to prove. Okay, well, how am I going to prove... let me just deal with them one at a time. I guess I'll just split my proof right now into two halves. So we will... Good to state my intention before I start a new paragraph. We will prove that A equals the empty set. So first, I'm going to do A is a subset of the empty set. You can do headings like this if you want. I'm actually going to write out the full deal right now since this is kind of new. Okay, so first I'll prove this, and then the second half of the proof will be this. Okay, A is a subset of the empty set. So let me focus on that goal and then come back to that one. So we'll come back to this goal later. A is a subset of the empty set. That means I need to prove that for all elements of A, they are elements of the empty set. Okay, interesting. To prove a universal like that, I should do a UG, universal generalization kind of argument. So consider any, and I can say consider any Z, now assume that Z is in A. How about consider any Z in A? Do that all at once, like we did in the previous lecture. Now I must prove that Z is, typo there. I must prove that Z is in the empty set. Okay, well, how can I conclude anything like Z is in the empty set? That should feel wrong, right? I mean, we just proved that nothing is in the empty set, right? That was Theorem 12. So how am I going to make an argument from Z and A to reach Z is in the empty set? This is super weird. I hope it feels a little weird. All right, well, we not only know that... Okay, let me put it this way. Our goal actually is to prove this implication, right? So we could prove this implication by assuming the hypothesis, assuming Z is in A, and then trying to prove Z is in the empty set. Or we could prove this implication to be true if the hypothesis is false, right? If we disprove the hypothesis, then we prove the implication. That's how implications work. Now, there's nothing wrong with our approach here. If we continue with the approach we're currently going with, then we're going to end up saying, okay, consider any Z in A. Well, since nothing is in A, according to our assumption here, in particular, Z is not in A. Therefore, we reached a contradiction. Since we reached a contradiction, we can now conclude anything we want because of this derived rule that says from a contradiction, you can conclude anything that you want. And we choose to conclude Z is in the empty set. We can conclude anything we want, so we can conclude this if we want. So that would be one way to go, but that's really very awkward. It would be much less awkward to just point out right away that this hypothesis of the implication that we're going for is false. And so the implication is vacuously true. So I'm not going to consider any Z in A. I'm going to consider any Z. I'm never going into the step where I say assume Z is in A. So in other words, even though this here is the suggested way to prove an implication, and it is the the way to prove an implication if you follow only the basic rules. I'm not going to do this. I'm going to prove the implication by relying on the idea of vacuous truth, which was established using the basic rules earlier. That was back when we were looking at the truth table for implication. Okay, so consider any z. Since nothing is in A, we have in particular, so this is universal instantiation, we have in particular that z is not in A. Right? Universal instantiation lets me conclude this with x replaced by anything I want. So I replaced x by z. Therefore, this implication, which has as its hypothesis z in A, is vacuously true. Is vacuously true. It follows, so this is the rest of the universal generalization. It follows that for all z, z in A implies z is in the empty set. And that's it. That's what was needed to prove this. Okay, let me create some space here. This is going to be a new paragraph. So these should really be separated with some space between them. All right, so let me get rid of this. I'm done with that goal, so that has served its purpose. Now let me section that part off and focus on this goal instead. This goal, empty set subset A, I need to prove that for all z, z in empty set implies z in A. And I think I can use a similar strategy, except I will not make use of this. Instead, you will see. So consider any z. Now, I want to prove that z in empty set is false, so that the implication becomes vacuously true. This is not going to help me. Instead, what's going to help me is, where is it? Oh, here. Theorem 12. Theorem 12 says nothing is in the empty set. So according to Theorem 12, well, technically Theorem 12 just says x specifically is not in the empty set. But thanks to that derived rule 31, this free variable can be replaced by anything when I apply this theorem. So Theorem 12 says that z is not in the empty set. By Theorem 12, z is not in the empty set. Therefore, this implication, z in empty set implies z in A, is vacuously true. The hypothesis is false. You can see I'm cutting out some typing from the recording here. And so it follows that for all z, z in empty set implies z in A. So that was the universal generalization. Starts here and ends here. And that's it for the proof. I guess to have a nice concluding sentence, I should mention that these two inclusions are sufficient thanks to Theorem 10, that theorem we mentioned earlier. It says double inclusion gives you equality. Usually you don't really need to say that. That's another really commonly used one. But how about I write it up here by using Theorem 10. Then I don't need to repeat myself so much at the bottom. Okay, that's it. So the empty set is the only set that is empty. So Theorem 12 says it is empty. Theorem 14 says nothing else is empty. If you have something else that's empty, if you thought you had something else that's empty, it's in fact just another name for the same thing, the empty set. So one interesting thing to notice about this proof is that when we proved this inclusion, we needed to use our assumption here, right? What we were proving is this implication. To prove this inclusion, we needed to use the hypothesis in the implication, so we needed to use this assumption. However, to prove this inclusion, we did not need that assumption. We could just use Theorem 12. So if we section this part off, this can be its own proof that the empty set is a subset of A without any assumptions about A. Without any assumptions about A, so for arbitrary A. So, in other words, this can become its own proof that the empty set is a subset of any given thing. And this is how things are divided up in the notes. So there's this Theorem 13 that I haven't mentioned, that I kind of skipped, where part of it says, yeah, the empty set is a subset of any given thing. And this is called minimality of the empty set. Or that's just the title that I'm giving it, because it's sort of saying that the empty set is, in some sense, in the sense of inclusion, it's the smallest set. It's the smallest set. It's inside, not in the sense of membership, but in the sense of inclusion, it's inside every set. And this is another component to the idea of minimality. This is saying, if anything else were inside it, then that thing would just be equal to it. So I will have you read through Theorem 15 on your own, but I just want to look at the statement. When you know a set is non-empty, that tells you that that set has an element. So that's really nice, and we use it a lot. Very often, in many theorems, you will see a hypothesis saying, assume this set is non-empty. Then, knowing it's non-empty, knowing something is not equal to the empty set, tells you that in your proof, you're allowed to use existential instantiation and get an element.